Hello and welcome to this third session on symmetry in chemistry. And this time we're going to look at some extremely symmetrical molecules. So in the previous couple of sessions we were looking at chirality. And so chirality, really these are the chiral molecules, are the ones with extremely low symmetry. So you remember those ones had no mirror symmetry at all, indeed no improper axis of rotation whatsoever. So those are remarkably low symmetry molecules. Now to look at the other end of the spectrum, really the most symmetrical molecules are those that have the shape of Platonic solids. So these are really the most symmetrical solids, and so in these cases we have all vertices equivalent, all edges equivalent, all faces equivalent. And on the screen there we can see several examples of molecules which have these Platonic shapes. So on the left there we've got a tetrahedral molecule, methane. Then we've got something like SF6, an octahedral molecule. Then next up we've got cubane. So far we've got a tetrahedron, an octahedron, a cube. And then on the right there, this is actually the simplest possible fullerene. This is a C20 cage where the atoms are at the corner positions of a dodecahedron. Now those are 4 Platonic solids. There is actually a 5th Platonic solid, the icosahedron, a 20-sided shape. Unfortunately there are no simple molecules which are icosahedral, perhaps not totally surprising given that you've got equilateral triangles as faces. I think you can find some kind of icosahedral kind of elements of more complicated structures, but certainly we don't see them in simple molecules. Now in actual fact we did look before, when we were looking at when we first started looking at different types of symmetry element, we did consider the octahedron and we found a whole load of symmetry elements. These are extremely symmetrical molecules. There are over 30 symmetry elements there. And in fact this earlier point I made on the slide here is that these Platonic solids are really quite unlike most molecular symmetries we come across. Normally a molecule has got a single principal axis around which there's the greatest symmetry, and then it'll be given some kind of symmetry label based on its properties around that principal axis. But in fact these Platonic solids, these very symmetrical ones, they've got multiple equivalent principal axes, and for that reason they tend to get special labels that reflect this very, very high symmetry. And as you can see there, we've got these very large number of symmetry elements with the octahedron, and it's quite interesting. It'll be interesting to compare this with the other Platonic solids, and this is what we're going to go on and do now. So first up, the tetrahedron. So this would be the lowest symmetry of the 5 Platonic solids, and an interesting way of looking at a tetrahedron, which is actually a very helpful way sometimes, is that you can actually fit a tetrahedron inside a cube. And this is what we can see on the right hand side there, the right hand image. So you can see on the right hand image that that object with different colours for its faces inside the cube has got each vertex on one of the corners of a cube. So obviously a cube has got 8 corners, 4 of them are going to be occupied by the tetrahedron's corners. And you can see when you consider the 4 corners of the tetrahedron mapped onto the cube, you can see they're all related to each other. They're all diagonally opposite on a face. So it's a bit like, every other corner on the cube is occupied. And so this, again, it reflects the very high symmetry of the tetrahedron. And so a little exercise is, how many symmetry elements can we see of the tetrahedron? Of course they're going to be quite a lot with all the equivalents of the vertices, edges and faces. You might like to pause the video for a second, have a think about it, note a few of them down, and I'll give you the answer in just a moment. So here we are on the screen. I'm afraid I've omitted to put the identity element, a bit like I did before with the octahedron, I'm afraid, as it's something that every single symmetry is associated with. I don't always bother. But it's interesting, if we look at the number of each of these types of element, that gives us, I think, some insight into what they're all about, how they fit with the structure. So we see it's got 4 C3 axes, 4 threefold rotation axes. Well, of course, the tetrahedron has got 4 faces. and all the faces are equivalent. So perhaps it's not surprising that each of these threefold axes goes through the centre of each face and connects up to the corner behind the face. And this reflects the fact that we've got equilateral triangles for faces, so we might expect a threefold rotation symmetry. And then the next one, the 3C2. Now this is where I think putting the tetrahedron inside the cube is helpful, because of course a cube, we can imagine with a cube the edges lining up with the x, y and z axes. And so these three axes here, each of them is going to hold one of the C2 axes, the twofold rotation axes. So in fact, each of these axes will bisect one of the edges. Perhaps another way of looking at it is looking at the tetrahedron. A tetrahedron has got it's got 6 edges, hasn't it? And so what happens is each of these C2 axes is going to bisect 2 opposite edges. And actually the edges there, so if you consider the edge on the far right, the edge that is between the green and red face, if you put an axis through the middle of that, going through the tetrahedron, it can actually come out there halfway along the left hand edge of the blue face. And it's interesting to see those edges are at 90 degrees to each other, the one on the far right and the one on the far left. And that actually leads to the next type of symmetry element, the S4. And this is something that we're going to see a bit more of, having an improper rotation of twice the order of a rotation. So you can see on that right hand edge, if you rotate that 90 degrees and then reflect it in a perpendicular mirror, it will then map out on top of the edge on the left hand side. And so we get one of these improper rotation axes again on each of the Cartesian axes. And then finally we have 6 of these sigma Ds, and these are the mirror planes. And so this reflects the fact that each of the 6 edges on the tetrahedron, you can cut it, you can bisect it with a mirror plane and reflect the tetrahedron through the mirror plane. And so that gives you the origin of the 6 there. But what I think is most interesting about the symmetry elements of the tetrahedron is the symmetry element that's not there. A very common symmetry element, amazingly, is absent from this highly symmetrical shape. I wonder if you've realised what that is yet. It's the centre of inversion symmetry. There's no centre of inversion on a tetrahedron, quite remarkably. We'll find it on all the other Platonic solids. Now, the tetrahedron we've looked at, that's one of the Platonic solids. The other 4 Platonic solids kind of come in pairs. And these pairs are called duals. And there's an interesting connection between the two. And that is that if you take the centres of the faces of one of these Platonic solids and connect up those face centres, you actually end up with a different Platonic solid. And this should be evident in the 2 sets of pictures on the screen here. So on the right hand side, it's fairly clear there that we've got a cube. A cube has got 6 faces, and if you join up the centre of those 6 faces, they become the 6 corners of an octahedron. And then on the right hand side there, we see that once you take the octahedron and then you connect up the centre of the 8 faces, you get the 8 corners of a cube. So you have this kind of beautiful symmetry. And so what you find is looking at these duals, and that is the number of the faces and the number of the vertices kind of alternates. So in the cube, we've got 8 corners, 6 faces, and in the octahedron, we've got 8 faces, 6 corners. And interestingly, these pairs, they share the same number of edges. So in both cases, we're looking at 12 edges on those 2 Platonic shapes. And then probably perhaps slightly more difficult to see are the highest Platonic solids, the dodecahedron, which we mentioned with the C20-fullerene, and the icosahedron. This is what we see on the left-hand side. And this quite pretty little model here makes this point that you see that the dodecahedron, this is the one inside, the solid shape inside the cage, you can see that the faces there are regular pentagons, and you can see that the corners appear in the centre of the equilateral triangles that make up the icosahedron, which is the cage molecule on the outside. So again, this reflects here the fact they are duals. So in the case of the dodecahedron inside, so in that case we've got 12 faces and we've got 20 corners. And so, not surprisingly then, when you look at the icosahedron, we've got 20 faces and 12 corners. And those two Platonic shapes share the same number of edges. So in both cases, 30 edges. And in fact, the number of edges kind of works out when you consider all the different faces. So for example, the dodecahedron there is made up of 12, that's the dodeca, isn't it? So it's made up of 12 pentagons. So each pentagon there will have 5 faces. Beg your pardon, each pentagon has got 5 edges. And so if you multiply the 5 edges by the 12 pentagons, you get 60. You might think 60 edges. But actually we've counted every edge twice, because each edge is shared between 2 pentagons. So if you take that 60 and divide it by 2, you get the 30 edges there on the dodecahedron. And I suppose you could do the same thing for the icosahedron. So for the icosahedron, you've got 20 faces. Each face is an equilateral triangle. So 20 faces times 3 edges is 60. But each edge is shared between 2 faces, so we divide by 2. And that gives you 30 edges. And I suppose it does follow, doesn't it? They have to have the same number of edges, because remember the relationship between the number of faces and the number of vertices, these are simply duals, one of the other, and they just alternated. Right, and so next up, how the symmetries of the cube and the octahedron related. Well, it turns out because of the kind of mirror that we have between the vertices and the number of faces, it works out that in fact the symmetries are identical between these pairs. So the cube and the octahedron share all the same symmetry elements. The dodecahedron, the icosahedron share all the same symmetry elements. And then here, a bit of a trick question. What is the dual of a tetrahedron? So if you take the centres of the 4 faces, connect them all up, as you probably realise, you get another tetrahedron. So a tetrahedron is, if you like, self-dual. Now, onto a new class of shape, and this is the so-called Archimedean solid. And these Archimedean solids are connected to duals, and actually these can be very relevant for our discussion of molecules coming up in a moment. So in fact we can actually arrive at Archimedean solids, or at least the ones we're interested in, we can arrive at them from Platonic solids. And so in Archimedean solids, all vertices are equivalent, but we can't say that all faces and edges are equivalent, but we can say that all faces are regular polygons. So if we look on the screen here, what we have in the centre is a cuboctahedron. So in fact, if you look at the left-hand object, you can perhaps appreciate that the left-hand object is essentially an octahedron with its 6 corners sliced off. And where each corner is sliced off, you can see that red square underneath. On the far right-hand side, I think you can appreciate there, that's a cube with its corners sliced off. And where each corner's been sliced off, we've got this yellow face showing underneath. And what's interesting is that where we've sliced off the 2 corners from each slice off the corners from the duals, if you keep, as it were, trimming them back and back and back, they kind of meet in the middle, as it were, with this shape called a cuboctahedron. So it's kind of part cube, part octahedron, where they've both been trimmed back. So you can see how the, those red squares on the left-hand side have kind of grown and grown and grown until it's met up with a red square from another truncated corner. So a cuboctahedron ought to have the same symmetry as both a cube and an octahedron, as it's sort of built up from those solids. And the reason I mention this is that this is actually quite a significant geometry in chemistry when we look at the solid state. So in metal structures, where you have so-called close packing, this is where you can imagine lots of spheres of the same size all packed together like sort of oranges in a box. And as those spheres all pack together, and you see this, for example, if you slide together lots of identical coins on a table, you'll see that each coin is surrounded by a hexagon of neighbours. And so what we find is that these atoms form these planes with this sort of hexagonal motif. And then when you stack those planes on top of each other, you end up with a three-dimensional so-called close-packed solid. And one of the ways you can arrange them in three dimensions is actually giving you a cubic arrangement. And what's really nice about this picture on the screen, firstly, on that middle shape, that in fact gives you the geometry of all the neighbours in this close-packed cubic arrangement. And one of the things that's curious about this is that when you consider it in a kind of cubic framework, you kind of struggle to see the hexagonal origin of it in the hexagonal close packing. But what's nice about the way we look at it on the screen is that when you look at the truncated octahedron on the left-hand side, from which we make the cuboctahedron, there you can see the hexagons are evident. And so actually those hexagons, you can think of them as relating to the kind of close-packed atoms. But actually, really, in these sessions, I'm not really wanting to spend any time on solid state, to be honest, so I'm not going to talk any more about that. We'll just keep pressing on with the molecular case. So yeah, that's that point about the hexagonal planes. Now, one thing that is interesting is that while we don't have any icosahedral molecules in chemistry, we do get quite close to that with C60. And again, it's in the context of duals. So we can form C60, and this is Buckminsterfullerene, that famous allotrope of carbon, which is kind of football shaped. We can create that from an icosahedron through this process of truncation. So in other words, it's kind of intermediate between the icosahedron and the dodecahedron. And this is what's illustrated on the screen here. Dodecahedron on the left, icosahedron on the right. And then we've got that truncated icosahedron next door to the icosahedron. This actually is our C60 molecule. So it shows this icosahedral symmetry, which of course is the same thing as dodecahedral symmetry, as those two are duals. And it's interesting this, because when you look up the symmetries, for example, of the icosahedral group, if you like, or the symmetries of the dodecahedron and the icosahedron, first of all, they're extremely large in number, of course, because it's such a symmetrical shape. And some of the symmetries can be quite difficult to see. And it struck me, of course, given that the icosahedron and the dodecahedron are both described by these symmetries, we could use either molecule to find the symmetry elements. And actually, this is quite a good plan, because it can make life a lot easier finding some of these symmetry elements. So, for example, when you look up what all the symmetry elements are in the dodecahedron / icosahedron, you find that there are 10 C3 axes. Now, I think, speaking personally, those are very difficult to see in a dodecahedron, but I think they're very easy to see in an icosahedron. Because, of course, an icosahedron is made up with equilateral faces, equilateral triangle faces, and, of course, there's 20 of them. And so all you need to do is take opposite faces. So there are 10 pairs of opposite faces, put an axis through them, and of course it's an equilateral triangle, so you've got threefold rotation. It's very easy to see the C3 axes when you're looking at an icosahedron. And of course, another symmetry element that we see, the highest symmetry element actually, are the C5 axes, these fivefold axes. These are very easy to see, of course, in a dodecahedron. Because of course the dodecahedron's got 12 faces, 12 pentagons. We just simply take 6 pairs of pentagons opposite each other, put an axis through the middle, and those are our 6 fivefold axes. So yeah, so far so good. One of the curious things is that these sort of n-fold axes we can associate with these improper rotations of 2n. And the reason for that is that in both of these shapes we've got these polygons with an odd number of sides. We've got a pentagon in the dodecahedron, we've got equilateral triangle in the icosahedron. And in fact, when you look at the opposite face, the face is the other way up. And so that way they won't simply have a simple mirror plane between them, but you'd have to give it a rotation of of an order twice that of its rotational symmetry, then reflect it in the perpendicular mirror to take it to the back face. And that's so we find in both of these objects we've got these S2n axes where it's double the order. And the other thing is we've got these 15 twofold axes, these C2 axes. And I think that's fairly easy to appreciate actually on either object, because they've both got 30 edges. And so what we need to do is consider the 15 pairs of opposite edges, and there should be a C2 axis that bisect each of those. Now, looking at Buckminsterfullerene in a bit more detail. So we've got a picture of the molecule on the right hand side, and what we've done in this particular case is we've added on the bonds, all the double bonds. So you can see in the molecule we've got these pentagons and hexagons, but of course each vertex is common to 3 faces, and so you might think that each vertex is associated with 3 chemical bonds, but of course carbon's got a valency of 4, so that implies that actually every carbon in the structure has to be associated with some kind of pi bond. And in fact we can see that in the illustration here. So you can see actually that all the pi bonds are associated with the hexagons in the structure, and all the hexagons have alternate single and double bonds like we see in benzene, whereas the pentagons actually are only made up of single bonds. So it's interesting this as far as this structure is concerned, like I say, it's an Archimedean solid, so actually all of the corners are equivalent. So actually every single corner in this structure is associated with 1 pentagon and 2 hexagons. And when you look at all the double bonds there are between the hexagons. So that's how it's all bonded together. And in fact it's interesting when we consider the geometry of these shapes, because of course hexagons, they have an internal angle of 120 degrees, which means the hexagons tessellate. So when you put hexagons together, so 3 hexagons can join together at a point, and of course 3 times 120 degrees is 360, and that shows that pentagons can just cover a flat plane. But it's a different story with pentagons. What happens if you just have 3 pentagons fused together? Now of course the curious thing about Buckminsterfullerene here is that we don't have pentagons touching other pentagons. The pentagons actually are only touching hexagons, and as it happens we've got the simplest possible structure in which no pentagons are touching other pentagons. And but if we consider the case where we just had 12 pentagons in the dodecahedron, then when you think about the internal angle on a pentagon, that's 108 degrees, isn't it? And so if we push 3 pentagons together, those 3 angles add up to 324 degrees. And of course that is 36 degrees short of 360. And so you can kind of think about where those 3 pentagons meet together, those 36 degrees short that it is of covering the plane leads to the whole thing leaving the plane and creating some curvature. And so we can think about 3 pentagons as it were leading to 36 degrees of curvature. Now, how much curvature do we need to close the cage? I mean, certainly in 2 dimensions, in 2 dimensions we can think about, as it were, closing the shape with 360 degrees. And of course, 360 degrees, the circumference of a circle, that's 2 pi times the radius. In fact, we'd call 360 degrees 2 pi if we were measuring it in radians. But actually, once you move into 3 dimensions, we're now talking about the surface area of a sphere. And of course, the surface area of a sphere is 4 pi r squared. So r squared, that gives you an area. And the 4 pi actually relates to, as it were, the solid angle, analogous to the way 2 pi did in the case of the circumference of a circle. So actually, when it comes to the angle of curvature for a sphere, you're actually looking at 4 pi, and that's 720 degrees. So when 3 pentagons come together, that point, as it were, gives you 36 degrees of curvature. We need 720 degrees of curvature to close the cage, and of course 720 is 36 times 20. So that means we need 20 vertices of these pentagons to close the cage. And so this really is why the dodecahedron, which is made up of pentagons only, is why that shape has got 20 corners, because each corner provides 36 degrees of curvature. And it's a 12-sided shape because you could say that each pentagon has got 5 corners. 12 pentagons times 5 corners is 60, but each corner is shared between 3 faces. So 60 divided by 3 is 20. And so that's your 20 vertices in the shape. And this is interesting because this is a general result actually, and of course there's a whole family of fullerenes, Buckminsterfullerene being the most famous, C20 being the most simple. Both shapes have got 12 pentagons, and in fact it's a general statement that 12 pentagons is required for closure of the cage. So in any kind of fullerene, as long as it's a closed cage, you'd be expected to find 12 pentagons. Now of course hexagons don't introduce any curvature, so actually you could have any number of hexagons. It doesn't really matter how many hexagons you've got. The crucial thing is you've got 12 pentagons, and this is a common feature of these related molecules. And so, as I mentioned before, C60 is the simplest type of fullerene where pentagons are not touching other pentagons. So C60 is remarkably stable. It's the most stable of the fullerenes. And this relates to the fact actually that when the pentagons touch each other, they're slightly less stable. So C60 would be more stable than C20. And so being Archimedean, as I said, you've got a common type of vertex. But we do have 2 types of bond in this structure. So we've got the bonds that are shared between a pentagon and a hexagon, and we've got the bonds that are shared between a hexagon and a hexagon. And you can see on this structure here that the hexagon-hexagon ones are double bonds. And of course, this turns out to be entirely consistent with the structure because we find that those hexagon-hexagon edges are shorter, because you'd expect a double bond to be shorter than a single bond. And now looking at in a little bit more detail at the Buckminsterfullerene, and so as you can see they're just illustrating the fact that this is the exact shape of a sort of classic soccer ball. And yeah, there's a wonderful story relating to Sir Harry Kroto, who was one of the scientists who discovered these in the first place, about how he was pondering how a 60 carbon molecule could be so much more stable than all the other types of molecule that he detected, but in much smaller degrees. So the story was he was sitting in his garden one day, and his kid kicked a football and it landed in his lap, and he had a kind of eureka moment holding the football. And so yeah, we've got that similarity there. But you see, I just mentioned, didn't I, that all these 6-membered rings had alternating single and double bonds, so they look like benzene. And so that raises the question, is C60 aromatic like benzene? Is that sort of like a giant benzene aromatic molecule? But one of the things about benzene is that its number of carbons, 6, is an example of a Huckel number, 4n plus 2. So these are the aromatic numbers of carbons, or if you like, more strictly, the aromatic number of pi electrons. So when n equals 1, that gives you 6 for benzene. When n equals 2, that gives you 10 for naphthalene. When n equals 3, that'll take you up to anthracene, the next one up. And so we have this series of sort of polycyclic aromatic hydrocarbons. But unfortunately, C60 does not fit the Huckel number. And so it's curious that there is a tendency, or there is some tendency of Buckminsterfullerene to form ions, and so it would need to form a 2 plus or a 2 minus ion, therefore to have an actual Huckel number. And in fact, it's interesting, you can see this on the title there, is 60 a magic number? Well, I don't know if you've come across this term magic number before. Magic numbers are particularly popular actually in the context of nuclear particles. You talk about magic numbers of protons and magic numbers of neutrons, and some nuclei being doubly magic because they've got a magic number of protons and a magic number of neutrons. So magic number is kind of that's in the sort of nuclear physics parlance. And I suppose in chemistry, if you talked about magic numbers, we'd normally be thinking about, for example, noble gas numbers of electrons. That's like a magic number. That's obviously the noble gases are the most stable atoms, and so we can think of those numbers as being magic, the number of electrons of the noble gases. And it's interesting because you can kind of use this analogy when you look at Buckminsterfullerene, because you can say that the molecule, it's nearly spherical. We could consider it to be a hard sphere. And the interesting thing is that if you're modelling the electrons on a hard sphere, actually you would end up modelling it using spherical harmonics. And so the spherical harmonics are, if you like, functions that describe a vibrating sort of rubbery sphere. But these are also the functions that we use to describe subshells in our model of the atom. So of course in an atom it's not just a hard sphere, but you've got a variable distance from the nucleus as well, which is where all the different shells come from. But if you had a hard sphere, you wouldn't have shells to consider, but you could use a subshell model. And so in fact we have these magic numbers corresponding to the subshells, where you fill each subshell successively. So 2 would be the first magic number, filling the S subshell. Then 8 when you filled S plus P. Then 18 when you filled S plus P plus D. And 32 when you filled S plus P plus D plus F. And of course these are the lengths of the periods in the periodic table. So as you know, as you go down each shell in the periodic table, you get an increasing number, one more each time, subshells. So the first shell just has S, the second shell's got S and P, the third shell's got S, P and D. Of course it's slightly more complicated than this in the periodic table because we have to consider the Aufbau ordering of subshells as well. But it's interesting that these are the kind of magic numbers that we have when we're considering Buckminsterfullerene as a hard sphere. Of course this is only going to be approximate, it's not really a hard sphere, but it's interesting to look at these models. And so we can see what kind of prediction we might make. So in fact it's curious, just looking at those numbers, 2, 8, 18, 32, what sort of mathematical sequence is that? Well, it's 2n squared, isn't it? Where n is, you can take n as successive integers. And so again, we can extend this pattern of 2n squared, and then the next ones are 50 and 72, which is a bit disappointing in a way, because we were hoping to see the number 60. It would have been nice if 60 was one of these numbers. We could say, oh look, that's why Buckminsterfullerene is so stable. It's a magic number. But it's kind of quite interesting in itself that it's not a magic number, because this makes us question the whole model. So in this kind of hard sphere model, this is assuming, I suppose, if you call it a hard sphere, we're assuming that the electron can kind of freely delocalize around the sphere so that we can treat it as a simple sphere. But if it's going to freely delocalize around the sphere, that would be to imagine that it was a kind of giant aromatic delocalized system. And so in fact we're fast coming to the conclusion that it's not just a delocalized system, because 60 electrons is neither a Huckel number nor a magic number from the point of view of the spherical harmonic subshell model. So why is it not fitting into all these models? And I would suggest the reason for that is that it's not flat. And so of course, if something's going to be properly aromatic and the electrons are going to be mobile, we see this from the very effective sideways overlap of p orbitals. But we get effective sideways overlap of p orbitals in a planar molecule. And all those polycyclic hydrocarbons I mentioned earlier, like naphthalene and anthracene, of course they're all flat. So that allows good sideways overlap and all the electrons migrating. But with the Buckminsterfullerene being curved like it is, that works against the aromaticity. So it's not really a properly aromatic molecule. There'll be sort of a bit of aromaticity, you could argue, I suppose, in the hexagons, but it doesn't really properly delocalize over the whole molecule. And actually you can see this a bit in the chemistry, because there is some tendency for addition to occur to those C-C double bonds. And of course you don't really expect addition to occur in aromatic systems, because they're trying to preserve their aromaticity. But of course those carbons, those benzene carbons, if they were to be aromatic, they'd be 120 degrees. There's a bit of strain where they're kind of pulled out of that planar arrangement. And in fact, when you have an electrophilic addition to these C-C double bonds, that will actually change the hybridization of the carbon atom. And so that can cause a certain amount of relaxation in the molecule. So it slightly reduces the bond strain when electrophilic addition occurs. So again, that's another reason to doubt the aromaticity of the molecule. Now, I can't resist mentioning C70, because we've just been looking at a soccer ball with C60, and C70, kind of its cousin, it's like the rugby ball. And so you can see here that what we've done is we've elongated the C60 molecule. We've kind of stretched it in one direction, and hence resembling the rugby ball, as we can see above. And so what we found is we've now given the molecule a unique principal axis, so the long axis there from left to right, whereas before with the Buckminsterfullerene, of course, being based upon a Platonic solid, it had multiple principal axes. It had 6 of those 5-fold axes. Now, I suppose you could say Buckminsterfullerene isn't strictly a Platonic solid, it's an Archimedean solid, but it does have all those symmetry elements of a Platonic solid. But much less so in the rugby ball. Now we've only got a unique 5-fold axis. Now we have 25 hexagons in the case of the C70. And actually I should have made the point before when we were looking at C60. Obviously it had 12 pentagons. All of these fullerenes, remember, have 12 pentagons. In the case of the Buckminsterfullerene, we had 20 hexagons. And remember we said that that was the smallest number of hexagons you could have, which would separate all the pentagons from touching other pentagons. And actually there's a good reason, if you think about it, why it has to be 20 hexagons. So when you think about the structure of C60, each pentagon, if it's not going to be touching another pentagon, that means all 5 faces of the pentagon have to be shared with a hexagon. So that central pentagon is touching 5 hexagons on each of its faces. And remember we said that with the hexagons, they had 2 types of edge. They were edge sharing with other hexagons, edge sharing with other pentagons. And so with the smallest number of hexagons, we would have to alternate the edges sharing with pentagons and sharing with hexagons to keep the pentagons apart from each other. So that means that each hexagon is touching 3 pentagons, half of its edges, and each pentagon is touching 5 hexagons with all of its edges. And so that gives you this 3 to 5 ratio there in terms of the number of these shapes. So when you think about 12 pentagons to 20 hexagons, that's your 3 to 5 ratio, isn't it? So that's this most simple geometry. Now, in the case of the rugby ball, we are looking to preserve a 5-fold axis. So it kind of makes sense that we add 5 hexagons, and those hexagons are distributed in a way that we've got a sort of 5-fold rotation connecting them all. And so actually, if you look at the picture there, you can see that, so you see right in the center of the picture there, we've got a hexagon with a pentagon on either side, but above and below it, we've got these double hexagons. And so I think this reflects effectively this sort of these extra hexagons that have gone into the structure. And having slotted in those extra pentagons, we've fixed the symmetry in such a way that on the principal axis, those pentagons at either end are actually going to be the same way up. Remember, they were the opposite way up in the case of the C60. And so for that reason, we actually lose the S10, the improper axes of rotation in the rugby ball. And so we've got this much simpler arrangement, the so-called D5H arrangement. So it's this dihedral symmetry where we've got a mirror plane connecting the top and the bottom pentagons. So we've managed to preserve a 5-fold symmetry axis, but we've lost the improper rotations, and we've only got a single one of these principal axes. But it's still quite a stable structure. So actually this is the second most stable of all the fullerenes. It's more stable than C20 because, like Buckminsterfullerene, this C70 still doesn't have any pentagons touching other pentagons.